Hi, I'm Dane Quinn at the University of Akron, and today I'd like to do another example modeling multi-degree of freedom systems using Lagrange's equations. And this is for fundamentals of mechanical vibrations. So here, this is a 2-degree of freedom system. We could define one coordinate that would specify the displacement of the block left and right. Then we could have a second coordinate that will determine the orientation of the bar with respect to the vertical. So it's a 2-degree of freedom system. So now let's look at the objects. One object is the block, right, so I'll go ahead and draw that. And then the second object will be the bar. Right, so let's go ahead and draw that. And of course these are pinned at the center of the block and the end of the bar. And now let's identify the forces. So here, obviously the weight due to gravity acts on both objects. Right, so we have W1 acting on the block, and then center of mass of the bar is here at the center. Right, and the weight there is W2. We also have a normal force between the surface and the block. Right, so that's going to be N. We have a spring force from the spring. That's Fs. And then finally we have a reaction force. So here the reaction force, let's say, is R acting on the block, which means that on the bar the reaction force has equal magnitude but opposite direction. So we'll write that as minus R. Now, if we look at this, the spring force and the gravitational forces are conservative. So that means they are derived from a potential function. Right, so I'm going to go ahead and put a little C there, and a C there for conservative. Now, in contrast, the remaining forces, the normal force and the reaction force, are constraint forces. In particular, they impose kinematic constraints. The normal force is there to make sure that the block doesn't pass through the surface, and the reaction force is there to make sure that these two objects stay pinned together. So here I'm going to put a little Z because we know that constraint forces do no work. This constraint force acts normal to the motion, and whatever work is done by this reaction force is compensated for by this reaction force, because these two things are of equal magnitude and opposite direction. Right? So essentially they cancel each other out. So now either the forces are conservative or constraints, so they do no work, and therefore the system is conservative. If there were forces that fell into that other category, namely non-conservative forces, then obviously we wouldn't have a conservative system. And the consequence of this is that all of the generalized forces vanish. Right? There are no generalized forces because all the forces here are either taken into account through the potential energy, or they do no work, so they don't enter into Lagrange's equations. Okay, so the next step is to define coordinates and directions. So here we can define directions I and j. That's horizontal and vertical. But then it'll also make sense for us to define a set of directions that are along the bar and perpendicular to the bar. So E1 here is perpendicular to the bar, E2 is along the bar. Now for coordinates, let's define the stretch in the spring, right, and we'll call that x. And then let's define the rotation of the bar as theta. In addition, we'll go through and identify the mass center of the bar as g and the connection point as b. So now we would like to turn to the kinetic energy. Well, the kinetic energy requires that we determine the velocities and the angular velocities of the objects, right? So for the block, the velocity is VB, which is x dot in the I direction. Again, x measures the displacement. For the bar, it's a little more complicated, right? Because we need the velocity of the center of mass. Unfortunately, we don't measure that directly, but we can determine that through the motion of the block and the rotation of the bar using kinematic equations that we learned in dynamics, right? So in particular, the velocity of g is the velocity of b plus the angular velocity of the bar cross r of g with respect to b. So here, this vector is r of g with respect to b. Again, it's the position of g with respect to b. So, filling in what we know, the velocity of b is x dot in the I direction. We've already said that. The angular velocity of the bar is theta dot in the k direction. And this vector, notice that it's in the minus e2 direction. And it has a length of L over 2. Right, so that's minus L over 2 E2. So now I can work this out, and we see that we have x dot in the I direction, and then k cross E2 is E1. And let's remind ourselves how we do that. E1, E2, and k, right? If I cross going this way, it's positive. If I cross going that way, it's negative, right? So k cross E2 is minus E1, but we also have another minus sign there. So those two cancel out, and we get L theta dot over 2 in the E1 direction. Now here, E1 is cosine of theta in the I direction plus sine of theta in the j direction. Likewise, we'll need this in a little bit. E2 is minus sine I plus cosine in the j direction. Again, we're writing these two directions in terms of I and j. So the velocity of g can be written in the I and the j direction as x dot, and then here E1 is cosine of theta. That's in the I direction. And then finally, L theta dot over 2 sine of theta in the j direction. Now, here's where we talk about linearization. Right? For small angles, sine of theta is approximately theta, and cosine of theta is approximately, and we'll do this actually out to quadratic terms, 1 minus theta squared over 2, and then of course higher order terms for both of these. Which means that when I go and look at this expression, cosine becomes essentially 1. There of course is a theta dot times theta squared term, but that's really small, right? Because both theta and theta dot are assumed to be small. Likewise, theta dot times theta is also assumed to be small, right? So those are negligible. And this becomes simply x dot plus L theta dot over 2 in the I direction. So to lowest order, this is the velocity of g. So now, the total kinetic energy is just the kinetic energy of the block plus the bar. So T is m1 over 2 times v dot v, so that's vb dot vb. This is the speed squared. Now for the bar, I have m2 over 2 times vg dot vg. Now that's the kinetic energy due to translation, plus 1/2 I of the bar times omega squared. And that's the kinetic energy due to rotation. So finally, we end up with m1 over 2 vb dot vb is x dot squared, and then we have m2 over 2 times vg dot vg, which ends up being x dot plus L theta dot over 2 squared plus 1/2 m2 L squared over 12. This is the moment of inertia of the bar about the center, times theta dot squared. So now look what happens. When we expand this piece out, we have an x dot term. We have an x dot squared term, actually. We also have a term that's proportional to x dot times theta dot. Right? So this piece becomes m2 over 2 x dot squared plus L over, well, just L times x dot theta dot plus L squared over 4 theta dot squared. Right, so that's this one term. So now some of these can be combined. We can combine this and that, and then we can actually combine this theta dot squared term with this piece here to get the total kinetic energy. Now we turn to the potential energy. The total potential is due to the spring. So that's V total is V due to the spring plus the potential energy due to gravity from the weight of the bar. Notice that we could include this weight for the block, but since the block doesn't move up and down, it doesn't change its height, right? So the change in potential there is equal to 0. I'm not even going to include this. We just have the spring and the weight on the bar. So here for the spring, it's 1/2 k x squared. Remember that x was the displacement of the spring. And for the gravitational potential energy, we get mgh, where h is the height above, and this is important, the ground of the center of mass of the bar. So notice that the bar freely hangs below our level of the ground. If I were to go over on this plot or this figure and figure out what h was, well, h here would actually be negative in this configuration because the center of the bar is below the ground. Go ahead and put a solid line there. So one way to find this is to take the position of G with respect to B. Remember, this is G and that's B. And then dot that with the upward direction J. So now when I do this, remember that R of G with respect to B was minus L over 2 E2 dot J. So here, this piece is minus L over 2 times E2. And we had said earlier E2 in terms of I and j, so that was minus sine I plus cosine of theta in the j direction dot j. And as a result, I dot j is equal to 0, and this becomes minus L over 2 cosine of theta. So here, using our small angle approximation, cosine is 1 minus theta squared over 2. So keeping quadratic terms here, we see this actually looks like a spring, right? Because the total potential energy is 1/2 kx squared plus now mgh, right? But h is minus L over 2, 1 minus theta squared over 2. So here we can write this as mg L over 4 theta squared, and then minus mgl over 2. This constant piece ends up dropping out from Lagrange's equations because we take partials with respect to the variables, and again, this is just constant. But this quadratic term, which comes from the gravitational force, actually looks very similar to the potential energy due to a spring. So for this problem, linearized, the effect of gravity is to add a restoring force, like a spring, to the motion of the bar. So finally, the Lagrangian can be written as shown. This was the kinetic energy, right? And here's that mixed term that we talked about. And then here is the potential energy that we discussed on the previous slide. So therefore, remember Lagrange's equations. They were d dt, the partial of L with respect to qi dot minus the partial of L with respect to qi equals the generalized force, which, because things are conservative, this equals 0. And for this problem, q1 we will choose as x, and q2 we'll choose as theta. So now we need to apply this for x and theta. So looking at the Lagrangian, and in particular the kinetic energy, the partial of L with respect to x dot is simply m1 plus m2 times x dot, plus now we have this mixed term, and that gives me m2L over 2 times theta dot. Likewise, the partial of L with respect to theta dot. So we have this mixed term, m2L over 2 x dot plus m2L squared over 3 times theta dot. Finally, the partial of L with respect to x, and this is minus now. Well, actually, when we take this partial, we have the partial of this term with respect to x. So that minus sign I'll actually pull over on the other side, right, because it matches up with Lagrange's equations. And we see this is k times x, and minus the partial of L with respect to theta is just mgl over 2 times theta. So we can now go and form Lagrange's equations. d dt, partial of L with respect to x dot, minus the partial of L with respect to x equals 0. So it's just the derivative of this with respect to time, right? So m1 plus m2 x double dot plus m2L over 2 theta double dot, and then minus a partial of L with respect to x, right? So that term is here. So plus kx equals 0. And the second equation, partial of L with respect to theta dot, partial of L with respect to theta, Now again we have this mixed term, m2l over 2, and that's times x double dot, because we're taking a total derivative with respect to time, m2l squared over 3 theta double dot, and then plus mgl over 2 theta equals 0. So here they are, right? These are the equations of motion. But if you're paying attention, we're actually on slide 5 of 6, so we'll do a little bit more. Here, I've rewritten those two equations, and so when I write this in matrix form, we see the following. The mass matrix becomes m1 plus m2, and then m2l over 2 times x double dot and theta double dot. Now if I go ahead and look at the acceleration terms in the second equation, we have m2l over 2 and m2l squared over 3. For the stiffness term, we just have k and then 0, 0, and then m2gl over 2. X and theta equals 0. So notice here that k is diagonal, right? So the system is statically uncoupled, but the mass matrix is not diagonal. We have some off-diagonal terms, so it's dynamically coupled. Now the other interesting thing that you may notice is that the mass matrix is symmetric. So symmetric matrices imply that M transpose is equal to M. And also in this case, K transpose is equal to K. It's diagonal, so it's definitely symmetric there, right? But the fact that the mass matrix is diagonal is interesting. And what we find is that that's always true. When we derive things with Lagrange's equations, both the mass and the stiffness matrices are diagonal. Now, if we go back and look at the Lagrangian, those diagonal terms come from these mixed pieces in the Lagrangian, right? So we would take, for example, in the first equation, the partial with respect to x, right? And we would basically get m2l over 2 times theta dot here, right? So let's actually put those in some sort of yellow boxes. So these two terms, which give rise to the off-diagonal pieces, come from the same place, right? So maybe it's not surprising that they should be the same, because again, they come from the same term in the Lagrangian. Well, this actually has important consequences later, but for now we'll just state it. When derived with Lagrange's equations, both the mass and the stiffness matrices are symmetric. And again, that will actually have important consequences when we go and talk about the solution for these kinds of systems, and in particular something referred to as modal analysis. right? So this is not just a coincidence. It's always true when we derive multi-degree of freedom systems using Lagrange's equations. We end up with symmetric mass and stiffnesses. So that's it for this problem. Thanks a lot, and I will talk to you again. Take care. Bye.